Hi students, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is to discuss the inverters formulas in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, direct notifications comes to mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So in this lecture, basically we are going to learn about the inverters. So in the inverters, we will learn about the first one is the classification of the inverters. So the classification of inverters. So we are going to classify the inverters based on two things. So based on supply. So based on supply, we are going to classify the inverters into two categories. So based on the supply, we are going to we are going to classify the inverters into two types: voltage source inverter and the current source inverter. So in the voltage source inverter, we are going to study about the single phase and three phase. In the single phase, we are going to study about the PWM inverter and also bridge. Whereas in the three phase, we are going to study about the 180-degree mode and also 120-degree mode. Other one is the series inverter and the parallel inverter. So these are the types of inverters we are going to study. So there are basically here, based on supply, we are going to classify the two types, and the remaining two are the series inverter and the parallel inverter. So overall, there are three classifications, which are the based on supply, series inverter and parallel inverter. So based on supply, we are going to classify the two types: voltage source inverter and the current source inverter. So classification of inverters, it is done in three types. So we can say it is the based on supply, series inverter and the parallel inverter. Whereas based on the supply, we are going to classify into two types, which are the voltage source inverter and the current source inverter. In the voltage source inverter, we are going to study about the single phase and also three phase inverters. Single phase, in the single phase, we are going to specifically study about the PWM inverter and also the bridge. Whereas three phase, we are going to study about the 180-degree mode and also 120-degree mode. So the first basic concept is the voltage source inverter. It's called as a voltage source inverter. The voltage source inverter means here we are going to use a voltage source. So if the input is a voltage source, then we are going to call it as the voltage source inverter. So basically, the main function of inverter is to convert DC supply to AC supply. So inverter basic function is to transform the DC supply into AC supply with the help of some circuit. So voltage source inverter is going to use the DC supply as the input. This is called as the stiff DC voltage is required. So requires freewheeling diode. So here we need a very stiff amount of DC voltage, means constant DC voltage is required. So in this voltage source inverter, we need the freewheeling diode. So stiff DC voltage is required, and also we require the freewheeling diode. Whereas the output voltage is independent of the load elements. See, no matter whatever the output elements, so you can go for any elements, but still the output voltage is always same for each and every load, but the output current depends upon the load. It's a very important statement. The output voltage will be independent of the load parameters, but the output current is going to depend upon the load parameters. And the output current is depend upon the load elements. Just now I have already told you. So voltage source inverter means this is a circuit diagram of voltage source inverter. In this, it requires a stiff amount of DC voltage at the input, or we can say constant amount of DC input voltage is required, and also it requires the freewheeling diodes, and I have already told you the output voltage is always constant, means it is the same voltage for each and every load, irrespective of the load elements. The output voltage is same at the output of the voltage source inverter, whereas the output current is going to depend upon the load elements. Now let us discuss about the current source inverter. So the current source inverter means here we need input as a DC current source. So input we need a DC current source. So practically we cannot make a DC practical current source. So we are going to use a DC voltage source and a large amount of inductor. So if you place in series combination of an ideal voltage source and an inductor, this overall is going to behave like a current source. So in the ideal, it's in practical we cannot make a current source. So here with the help of these things, with the help of this voltage source and this inductor, we are going to make a current source, because as the inductor value is very large, so the current will not changes, it will be always remaining constant. So because of that, this series combination of the ideal voltage source and an inductor is going to behave purely like a current source. So therefore stiff DC current is required at the input side. So the stiff DC current is required at the input side, and the output current is independent of load elements. So in the current source inverter, the output, or you can say the output current in the load, is independent of the load elements. No matter whatever the load elements, always the output current is always constant, or the diagram of the output current is fixed for each and every load, whereas the output voltage depends on the load elements, whereas the output voltage is going to depend upon the load elements. So for a current source inverter, basically we need an input of constant current source. So we can get that with the help of this ideal voltage source and a inductor in series combination. So because we are going to choose an inductor of huge value of inductance, so its current value will be always remaining constant. So because of that, we can say the series combination of an ideal voltage source and an inductor is going to behave like a current source. Here at the output, the load current is constant irrespective of the load. So irrespective of the load, the output current will be always remaining same for each and every load, whereas the output voltage is going to vary depending on the load elements. As the load element changes, the output voltage changes for this current source inverter. So let me do the revision of the voltage source inverter and the current source inverter. I have already told you, in a voltage source inverter, we need input and stiff DC voltage, and it also requires a freewheeling diode is required in the DC in the voltage source inverter, and the output voltage is independent, or the output voltage is independent of the load values, but only the output current is going to depend on the load elements. Whereas in current source inverter, we basically need an input of stiff DC current or the constant DC current that we can obtain with the help of an ideal voltage source and an inductor if we are going to make them in a series fashion. And here freewheeling diodes are not at all necessary. In this current source inverter, the freewheeling diodes are not at all necessary, whereas the output current is independent of the load elements. No matter whatever the load, the output current will be always same, whereas the output voltage is going to depend upon the load elements. This is some of the brief introduction about the voltage source inverter and also the current source inverter. So now let us discuss about the single phase half bridge voltage source inverter. Single phase half bridge voltage source inverter. So single phase half bridge voltage source inverter means, single phase means here we are going to give only single phase. So this is a single phase. Half bridge means here there is only one leg will be there. So this is called as the overall, this combination is called as the one leg. So if there are two legs means it is called as a full bridge, but here we are going to use only one leg, so it is called as a half bridge. And it is called as a voltage source inverter means converting a DC voltage into a alternating voltage. Simply we can say that we are varying constant voltage into a DC voltage to a AC voltage. So it is called as a voltage source inverter. So here single phase half bridge voltage source inverter. So this is the diagram of the single phase half bridge voltage source inverter, which is this is Vs by 2 and this is Vs by 2 and this is thyristor T1 and thyristor T2, and these are the freewheeling diodes D1 and D2. I have already told you the freewheeling diodes are used only in the voltage source inverter but not in the current source inverter. So therefore, this is the circuit diagram of the single phase half bridge voltage source inverter, and this is the load we are going to keep in this fashion. So this is the circuit diagram of the single phase half bridge voltage source inverter. So Vs by 2, T1, T2, D1, D2, and here there is a load in this fashion. Let me assume the output voltage is plus or minus V naught of T and the output current is I naught of T. So here we are going to use the switches which are fully controllable, means here by the user can control the on and also off of the switches. the user can control both the on and also off of the switches. So this is called as a fully controllable switch. Means the switches can be easily controlled by the user. Means he can turn on the switches and also he can turn off the switches. So these are called as a fully controllable switches we are going to use in the inverter. Now we are going to analyze what are the diagrams we are going to get at the output voltage and current we are going to see. Suppose if you are going to keep the resistive load. So this is the input voltage which is Vs by 2. So Vs by 2 is the input voltage for all the time as it is a constant voltage. So it will be always constant for all the time. So it is constant voltage for all the time. So now here we are going to turn on the thyristor T1 and T2 in a complementary fashion. So if one is on means the other is off. If other is off means the other one is on. Means we are going to do the complementary operation of the thyristors. If T1 is on means T2 is off. If T1 is off means T2 is on. So this is the way that we are going to do the operation of the thyristors. So let me assume the thyristor T1 is on. So when the thyristor T1 is on, then definitely I am going to turn off the thyristor T2 because the user can easily control it. So therefore, even when I on the T1 and I also have the T2. So by analyzing the circuit, we can simply say that the output voltage is equal to which is Vs by 2. So the output voltage we are going to get which is Vs by 2. So Vs by 2 is the output voltage we are going to get which is plus Vs by 2 we are going to get. So we are going to get plus Vs by 2 we are going to get, and the output current is V0 by R. So therefore Vs by 2R is the output current we are going to get in this region. And after some time I am going to turn off the T1. So if I turn off the T1 means I am going to turn on the T2. So if T1 is off means T2 I am going to on. So these are the complementary fashion. So if T1 is off means T2 I am going to on. So by analyzing the circuit, what you are going to get, if T2 is on, then V0 of T is equal to minus Vs by 2. So minus Vs by 2, and I0 of T is equal to V0 by R. So therefore you are going to get minus Vs by 2R. So this is the current you are going to get. So simply we can say that, see, this here T1 is on and here T2 is on. Same thing again you have to repeat the same procedure. If T1 is on, T2 is off. Same thing we are going to get. If T1 is off and T2 is on, same thing we are going to get. So this is the graph we are going to get. So this is a period. So after this it is repeating again and again. So this is called as basically output voltage and the output current you are going to get. So this is the output voltage diagram and this is the output current diagram. So you are going to get here. So you can see clearly here T1 is on. See, only T1 is on. So remaining all the switches are off. Here T2 is on. So therefore remaining all the switches are off. So same thing is going to get repeated. So this, the upper one indicates that these are the on and the down one indicates that these are the off. So we can say that here when T1 is on means the others are off. So for resistive loads there is no conduction of freewheeling diodes. So freewheeling diodes are not all conducted or they are always off whenever we are going to use the resistive loads. So if you want to find what is the average output voltage, the average output voltage is equal to 0 and also the average output current is also equal to 0 because the positive area is equal to negative area. So we can say that the average output voltage is equal to 0 and also the average output current is also equal to 0. But if you want to find what is the average output RMS value, the RMS value of the output voltage, if you want to figure out, which is equal to Vs by 2. So therefore simply we can say that the average value of the output voltage is 0 and the RMS value of the output voltage is equal to Vs by 2. So you can see clearly from this diagram only. So the average value of the output voltage is equal to 0 whereas the RMS value of the output voltage is equal to Vs by 2. So this is called as the average value of the output voltage is equal to 0 and the RMS value of the output voltage is equal to Vs by 2. So this is the same output voltage we are going to get. The same output voltage we are going to get irrespective of the load. See, this is the voltage we are going to get irrespective of the load for the single phase average voltage source inverter. But the current is going to vary depending upon the load parameters. So again I am repeating it, listen carefully. The output voltage diagram will be same irrespective of the load elements, but the current diagram is going to vary based on the load elements. So now we will go for the analysis of another load which is RL load. So for the same single phase average voltage source inverter, So now we are going to replace the resistive load by the RL load, and then we are going to do the analysis. So now the input voltage is Vs by 2, which is always constant for all the time. So let me take here, see now I am going to do the on and offing of the thyristors T1 and T2 in this fashion. So here I am going to on the T1, and here I am going to turn off the T2, and then I am going to off the T1 and also off the T2, and then I am going to turn off the T1, and then I am going to turn on the T2, and then I am going to turn off the T1, and then I am going to turn off the T2. So this is the fashion I am going to repeat after this time. So therefore on, off, 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 on, off. So this is the manner I am going to repeat after the same time, like periodic wave. I am going to do this one. So this is the onning procedure for the T1 and T2. I am going to follow this procedure for after the time of T for each and every cycle. So if T1 is on, if T1 is on and T2 is off, what I am going to get basically, if T1 is on and if T2 is off, then we can say that simply the output voltage is equal to Vs by 2. So the output voltage is equal to Vs by 2. If both are off, means what is going to happen? So we can say that now simply, so we can see clearly when T1 is on and T2 is off, what is going to happen? The supply means the voltage V0 is equal to Vs by 2. So output voltage is equal to Vs by 2. So therefore here RL load means the current in the inductor is going to get increased. So charging mode, so the current is going to get increased. So the current is going to get increased in this charging mode. Suppose if I off both the things. So now in the second case I am going to off the both the things. So both the T1 and T2 I am going to off. Then what is going to happen? Then the diode D2 is going to conduct. So the diode D2 is going to get conduct. So because the current in the inductor cannot change instantaneously. So therefore the current is going to decrease slowly. So because of that, the diode D2 is going to conduct in this region, and here the current is going to get decay. It is going to get decay. So therefore the diode D2 is going to conduct in this region. So therefore the current is now going to get decay in this region. So after that, so if the D2 is going to conduct, suppose if D2 is going to conduct, then what is the thing we are going to get? Then the output voltage is equal to minus Vs by 2. So the output voltage is equal to minus Vs by 2 we are going to get from the circuit, we can see clearly. So therefore now here this is the output voltage we are going to get. Then I am going to turn on the T2. So therefore I am going to turn off the T1 and turn on the T2. Then what is going to happen? Again the output voltage is equal to minus Vs by 2, and now the current is going to charge in the reverse fashion. So therefore the current is going to get charged in the reverse fashion. So therefore the current is going to become negative, means charging in the reverse direction. So it is going to get increase. So the current is going to charge in the reverse direction in this direction. So we can say this is the value we are going to get. So after that again I am going to off both the thyristors. So I am going to off both the thyristors. Then what is going to happen? Then D1 is going to get conduct. Then D1 is going to get conduct. So whenever the D1 is going to conduct, then the output voltage is equal to Vs by 2. So therefore the current is going to get decay slowly. So it is going to get decay slowly, and finally it is going to come 0. So this is the diagram we are going to get. Again after the same cycle, if you repeat this same process, same switching procedure, again you are going to get the same diagram. So the output voltage is same as the previous one, but now here we can see the waveform of the current is changed. In the R load, the current is following the voltage waveform, whereas here now it is in the triangle shape. So for R load it is a square shape. The current is in the square shape for the R load, whereas for RL load it is in the triangle format. So the current in the output for RL load it is in the triangular format. I have already told you in the first case T1 is conducting. So T1 is conducting means remaining everything is off. So here the current is charging. In the second case the D2 is on. So as the D2 is on means the remaining all switches are off. So therefore the inductor is now discharging. Similarly in this case the T2 is on. So when the T2 is on means the remaining all the switches are off. So therefore L is now charging in the reverse direction. In this case D1 is conducting. So therefore remaining all the switches are off. So we can say that here the inductor is now discharging. So this is the way that you need to analyze. So this upper arrow indicates that these all these devices are connecting here, and this one indicates that all these are off. So this is the way that you need to go for the switching in order to get the output voltage and the output current in this manner. Let me repeat this one again here. See, in the first case, the thyristor T1 is on and the T2 is off. So therefore, whenever the thyristor T1 is on, what is going to get? You simply if the T1 is on, then the output voltage is equal to Vs by 2. So therefore, when the output is equal to Vs by 2 means the current is charging. Whereas in the second case, simply here we are going to turn off both the thyristors. So whenever you are going to turn off both the thyristors means D2 is going to conduct. So whenever the D2 is going to conduct, so therefore simply we can say that V0 is equal to minus Vs by 2 and the current is going to get decay in the reverse fashion. So it is going to get decay. And after that, again you are going to turn on the T2 and turn off the T1. So whenever the T2 is on means remaining everyone is off. So therefore, now again the output voltage is equal to minus Vs by 2 and the current in the inductor is going to charge in the reverse fashion. So it is going to charge in the reverse fashion. And then what is going to happen is simply again the D1 is going to conduct. If D1 is conducting means simply we can say that the output voltage is equal to plus Vs by 2 and the current, and we can say the current is now going to get decay. It is going to get discharge. So the inductor is going to get discharge. So current is going to get decay. So this is the way you are going to get for the current waveform. So now we are going to analyze the single phase full bridge voltage source inverter. Single phase full bridge voltage source inverter. Single phase full bridge voltage source inverter. So this is a diagram of a single phase full bridge voltage source inverter. See, now there are two legs. So in this fashion there are two legs. So if there is a one leg means it is a single phase off bridge voltage source inverter. But if there are two bridges in the same format, then we say there are two bridges in this format, then we say it is a single phase full bridge voltage source inverter. And now the input voltage is Vs and the input voltage is now Vs. So if you keep the load in this region, it is called as off load, single phase off bridge voltage source inverter. If you keep here the load, then it is called as a single phase full bridge voltage source inverter. So this is the diagram of the single phase full bridge voltage source inverter. So T1 D1, T4 D4, T3 D3, T2 D2. So T1 D1, T2 D2, T3 D3, T4 D4. So this is the format that you need to go for the circuit, and you have to keep the load in this format by connecting all these dots. So let me take a load here, and the output voltage is plus or minus V0 of t and the output current is I0 of t. So I am going to assume all the switches are fully controllable, means the user can easily control and on and also off the switches. Everything is under the control of the user. So now for this single phase full bridge voltage source inverter, I am going to assume the load is a resistive load. So based on this, and now I am going to analyze what is the output voltage and the output current I am going to assume. So now this is a resistive load is I am going to keep here. So if I am going to keep the resistive load here, I am going to assume in the first region. In the first region, I am going to turn on T1 and T2. So I am going to turn on T1 T2. Whenever the T1 T2 are on, so you can see from the circuit diagram. So therefore the output voltage is equal to minus Vs. So output voltage is equal to minus Vs. So output current is equal to up to output voltage by R. So therefore minus Vs by R. So minus Vs by R. Whereas in this region, I am going to turn on the T3 T4. So whenever the T3 T4 are on, then the output voltage is equal to source voltage. So therefore we are going to get plus Vs, and also the output current is equal to output voltage by R, so which is plus Vs by R. So plus Vs by R. So this is the thing that you are going to get, and the same thing we are going to repeat it again. So we can say the output voltage is always a square waveform and the output current is also a square waveform. See, for R load, both the output voltage and the output current are going to have the same shapes, but for other loads they are going to get vary. So this we are going to call it as a square waveform. So here T1 T2 are on, then T3 T4 are on. So if T1 T2 are on means remaining all the switches are off. If T3 T4 on means the remaining all the switches are off. In this case, I have already told you the freewheeling diodes are not all conducting. They will be always off for pure resistive loads, but for other loads they are going to get conduct also. Suppose now I am going to keep the RL load. Suppose if I am going to keep the RL load and then I want to analyze what is the output voltage and also the output current I want to analyze. So now I am going to analyze what is the output voltage and the output current for the RL load. So if I am going to keep the RL load in this single phase full bridge voltage source inverter. So in the first case, I want to on the T1 and T2. So now I am going to on both the T1 and T2. So from the circuit diagram you can see, if you on T1 and T2, then the output voltage is equal to minus Vs, and the output current, or simply we can say that the output current is going to get charged in the reverse fashion. The current is going to get charged in the reverse fashion. So therefore the current is going to charge in the reverse fashion. And if you see, after that what you are going to see, basically you are going to turn off all the thermistors. Then the current is charging in the reverse direction. Simply means here the current is now going to flow through D3 D4. The current is going to flow through D3 D4. So whenever the current is flowing through D3 D4 means simply we can say that the output voltage is equal to plus Vs. So the output voltage is equal to plus Vs. So therefore here simply we can say that now the current is going to get decay. Now the current is going to get decay because of reverse fashion of the voltage we are going to apply. So the current is going to get decay, and finally it is going to become 0. So after that I am going to turn on the T3 T4. If I on T3 and T4, then we can say the output voltage is equal to Vs and the output current is going to get charged. So it is going to get charged in the positive direction. It is charging in the positive direction, and then I am going to turn off all the thermistors. So therefore simply we can say that the current should be always positive. So therefore it is going to flow through D1 D2. So it is going to flow through D1 D2. So because of that we are going to get a output voltage of minus Vs. So because of this negative voltage, the current is going to become now decay, or it is going to be discharges. So the inductor is going to get discharged in this region. So therefore here simply we can say that the current is going to get discharged. So this here, this output voltage is now square waveform, but the output current we are going to get a triangular waveform. So but the output voltage is square waveform, but the output current we are going to get a triangular waveform. So I already told you, in this region T1 and T2 are conducting, so remaining everything is off. In this region D3 D4 are conducting means the remaining every switch are off, and similarly here T3 T4 are conducting means remaining all the switches are off. Similarly here D1 D2 are conducting means remaining all the switches are off. I have already told you, here in this region the inductor is charging, and here the inductor is discharging, and here the inductor is charging, and here the inductor is discharging. So in this each switch operated for only T/4 period. So let me assume this is the overall time period T. So after this again it is repeating. So each switch is operated for only T/4. So T1 is operated only for T/4, and T2 is also operated for only T/4. Whereas D3 is operated for only T/4, and D4 is also operated for only T/4, and T3 is operated for only T/4, and T4 is also operated for T/4, and D1 is also operated for T/4, and D2 is also operated for only T/4. So therefore we can say that each and every switch in this RL load is going to operate for only T/4. So in this each diode operated for only T/4 period. So all the switches with the thyristors or with the diodes, all the things are operated for only T/4. So let me assume the frequency of the output voltage is equal to 1 by T. So the frequency of the output voltage is equal to 1 by T. Then what is the frequency of each switch, whether it is a diode or whether it is a diode or thyristor, both in any case. Or we can say it's basically a switch. These are the fully controlled devices. So let me assume this is a switch. So therefore the frequency of switches is equal to 4 by T, because their frequency is now 4 times, because they are going to operate for only T/4. So inverse of this is nothing but 4 by T, which is 1. 4 by T is nothing but 4 into F. So therefore simply we can say 4 times the frequency of this output voltage. And similarly the frequency of the diode is simply we have to go for the reverse of this, which is 4 by T. So therefore which is 4 into frequency of the output voltage or frequency of the output current. So therefore simply we can say that here F, the frequency of the switches, either switches or the diodes, which is 4 times the output voltage frequency. So which is simply this is the formula. Suppose if FV0 is the frequency of the output voltage, means the frequency of the each switch or each the diode is equal to, which is 4 into frequency of the output voltage or the output current. 4 times. It is 4 times of the frequency of the output voltage or the frequency of the output current. Now we are going to study what is the performance specifications of single phase half bridge voltage source inverter. Means we are going to analyze what is the things we are going to get after the for the single phase half bridge voltage source inverter. So we have already told you what is the circuit diagram of the single phase half bridge voltage source inverter, and then we are going to do some performance analysis. This is the output voltage we are going to get. So irrespective of the load, this is the output voltage we are going to get for a single phase half bridge voltage source inverter with a peak value of Vs by 2. So now I want to do the analysis. As it is a periodic signal, I want to write what is the expression of the output voltage in terms of Fourier series, which is sigma n is equal to 135 up to infinity. I have already told you the general format, which is 4 into the peak value is Vs by 2 by n pi sine of n omega t or n theta. So 4 into peak value, which is Vs by 2 by n pi into sine n omega t. So here peak value is Vs by 2. So 4 into Vs by 2 is again 2 Vs by n pi. So this is the thing that you are going to get. So sigma n is equal to 135 up to infinity 4 into peak value, which is Vs by 2 by n pi into sine n omega t. So finally you are going to get 2 into Vs by n pi into sine n theta. So this is the expression that you are going to get. And I want to find what is the RMS value of the fundamental component. The RMS value of the fundamental component is substitute n is equal to 1 here. The peak value we are going to get 2 Vs by pi by root 2. Then we are going to get the RMS value. So the peak value of the fundamental component of the output voltage is 2 Vs by pi. But if you want to find what is the RMS value of the fundamental component of the output voltage, peak value by root 2, then we are going to get 2 Vs by pi by root over 2. Simply we are going to get 0.45 Vs. So the RMS value of the fundamental component of the output voltage is 0.45 Vs we are going to get. And if you want to find what is the overall RMS value of the output voltage, it is equal to peak value, which is Vs by 2. And if you want to find what is the fundamental displacement factor, then as there is no alpha, so therefore alpha is equal to 0, there is no delay, so cos 0 is equal to 1 you are going to get. So G is called as the distortion factor ratio of the fundamental RMS component by the overall RMS value. So for the output voltage we are going to analyze. So the RMS value of the fundamental component of the output voltage by the RMS value of the overall output voltage. So if you do this one, because we know both the things, just go for the division, we are going to get 0.9. So 0.9 is the distortion factor we are going to get. And the input power factor is the multiplication of the distortion factor into fundamental displacement factor. As the G value is 0.9 and the fundamental displacement factor is 1, so 0.9 into 1 is again 0.9. So if you want to find what is the THD, which is equal to 1 by G whole square minus 1. So if you substitute here G and if you do simplification, finally we are going to get 48.3% is the THD we are going to get. So now we are going to do the performance analysis of the single phase full bridge voltage source inverter. I have already told you the single phase full bridge voltage source inverter diagram, and now we are going to do the performance analysis of the single phase full bridge voltage source inverter. As you can see clearly, this is the output voltage that we have already got here. So therefore this is the output voltage, the peak value of plus Vs and minus Vs. This is the output voltage we have got. So now we are going to do some Fourier analysis for this diagram. So as it's a periodic signal, then we are going to write the Fourier series of the output expression. We are going to get V0 is equal to sigma n is equal to 135 up to infinity 4 into the peak value is Vs by n pi into sine n omega t. So this is the expression that you are going to get for this in terms of Fourier series. So if I want to find what is the RMS value of the fundamental component of the output voltage, which is peak by root 2. So at n is equal to 1, the peak value is 4 Vs by pi by root 2. We are going to get the RMS value. So after doing simplification, finally we are going to get 0.9 Vs is the fundamental component of the RMS value of the output voltage, which is 0.9 Vs. And if you want to find what is the overall RMS value, so if you want to find what is the overall RMS value of this output voltage, which is equal to the peak value itself, which is equal to Vs. So you can see it clearly here, as the alpha is equal to 0, as there is no lagging or leading, so therefore simply we can say that it is equal to 0. So fundamental displacement factor is equal to cos of 0 is equal to 1. So if you want to find what is the distortion factor, which is the ratio of the RMS value of the fundamental component of the output voltage by the RMS value of the overall output voltage, So you know both the values. You know the RMS value of the fundamental component of the output voltage and the RMS value of the overall output voltage. If we do the division, we are going to get 0.9. So 0.9 is the distortion factor. So same value we have got for the single phase average voltage source inverter also. So whether it is a single phase average voltage source inverter or whether it is a single phase full bridge voltage source inverter, the distortion factor is independent of the peak value. So therefore it is again 0.9. Whereas the input power factor is the product of the fundamental displacement factor into distortion factor, as the G value is a 0.9 and the fundamental displacement factor is 1, so you are going to get 0.1, you are going to get. Whereas THD is equal to under root over 1 by G whole square minus 1. So substitute the value of G and doing the simplification, we are going to get 48.3%. So you can analyze two things from the single phase half bridge voltage source inverter and the single phase full bridge voltage source inverter, which is the distortion factor is same, which is 0.9, and also the input power factor is also same, which is 0.9, and the THD is also same, which is 48.3% for both the single phase average voltage source inverter and also single phase full bridge voltage source inverter. For this both of these circuits, it is same. So let me give a small important point in this single phase full bridge voltage source inverter. So in this single phase full bridge voltage source inverter, let me give a small important point. Suppose if you are going to keep some lagging load, then the current you are going to get in this format. Let me assume the output current for this lagging load I am going to get I0 is equal to Im into sine of omega t minus theta. So this is the output current I am going to get for this load. And Vs is called as the supply DC voltage, because as it is an inverter, then we are going to get the input is basically a supply DC voltage. Then I want to find what is the overall average power which is supplied by the source or the overall average power consumed by the load. So P is called as the power drawn from the source, or simply we can say that what is the overall average power supplied by the source or the overall average power which is absorbed by the load, which is both are same. And I0 is called as a basic load current. I have already told you I0 means the current in the load. So I want to find what is its power P. So P is equal to the simple formula, which is output RMS value into output RMS current into cos theta. So this is the cos theta. So output RMS current. So this is called as the fundamental component. So this is basically the fundamental component of the RMS value of the output voltage. See, listen carefully here. As output voltage is a periodic signal, so it is going to have so many frequency terms. So out of those frequency terms, you have to take only those frequency which is omega. So which is only omega. So therefore omega is nothing but it is the fundamental component. So therefore the RMS value of the fundamental component of the output voltage into the RMS value of this one current into cos theta, where theta is the angle between the fundamental component of the output voltage and this current. So therefore the RMS value of the fundamental component of the RMS value of the fundamental component of the output voltage is equal to 4 Vs by pi into root 2 into Im by root 2 into cos theta. So this is the amount of the average power consumed by the load or the amount of power which is supplied by the source. So simply we can say that here, which we are going to get the RMS value of the fundamental component of the output voltage into the RMS value of this current into cos theta. Theta is the, we can say it is the angle between the fundamental component of the output voltage and this current. This both the terms are going to have the same frequency omega. So this is the expression that we are going to get. So now we are going to analyze the pulse width modulation. So now we are going to analyze the pulse width modulation. So let me give a small idea regarding this pulse width modulation. See, this is an op amp. So this is basically an open, or you can say there is no feedback. So open loop op amp. We can simply say this is a open loop op amp. So therefore here is a plus non-inverting terminal and the inverting terminal. So there are two supply terminals. So one I am going to give it is plus VCC and the other one I am going to give it to ground. So non-inverting terminal I am going to give, we can say reference signal. So this is called as a reference signal. I am going to take only the absolute values. And similarly this is called as a carrier signal. I am going to take only the absolute values of this reference signal and the carrier signal. So reference signal I am going to give the non-inverting terminal. As a carrier signal I am going to give it to inverting terminal. So this output of this op amp we are going to give to a pulse generator. So we are going to give to a pulse generator. So therefore here For single phase half bridge rectifier or for single phase half bridge voltage source inverter. So for single phase half bridge voltage source inverter, there are two thyristors. There are only two thyristors. So we can get only Ig1 or Ig2. So these are the pulses. So these are the pulses we can get as the output, or we can say these are the gate pulses we are going to get in order to control these fully controllable switches. So these are the gate pulses we are going to get, which is output of this pulse generator. So with the help of this we can control the switches in the single phase half bridge voltage source inverter, because in the previous circuits whatever we have seen, the average value of the output voltage is constant, so we cannot vary them, but we want to vary them. So therefore if you want to vary, then you have to control these gate pulses. If you control these gate pulses, then only you can control the overall output voltage average value you can control. So if you control this gate pulses switching, then you can control the output voltage average value also you can control. So that is the reason we are going to generate the Ig1 and Ig2. Similarly, if you want for single phase full bridge voltage source inverter, there are four thyristors T1, T2, T3 and T4. So the first output of this pulse generator we are going to use for Ig1 and Ig2, and the other output we are going to use for Ig3 and Ig4. So we can say that here these are the two used for both single phase half bridge voltage source inverter, and these two we are going to use for single phase full bridge voltage source inverter. So with the help of this controlling of the switches, then we can easily control the output voltage. As you control the output voltage, then the average value also you can easily control. So VR is called as the reference signal, whereas VC is called as the carrier signal. So VR is called as the reference signal and VC is called as the carrier signal. So reference signal can be either square signal or sine signal. So reference signal can be either square signal or the sine signal, whereas the carrier signal always we are going to use the triangular signal. So a reference signal either it can be square signal or the sine signal, whereas the carrier signal is always triangular in shape. So this is the thing that you need to remember. So the reference signal can be either square signal or the sine signal, whereas the carrier signal will be always in the shape of the triangular. There are different types of modulations. Let me tell you, the first one is single pulse width modulation. In the single pulse width modulation means only we are going to get one pulse, means the output we are going to get only one pulse in a half time period. In 0 to pi we are going to get only one pulse width we are going to get in the output of the output voltage in a period of 0 to pi, that we are going to call it as a single pulse width modulation. So here reference signal we are going to take it as a square signal. So here we are going to take the reference signal as square signal, whereas the carrier signal we are going to consider the triangular waveform. Whereas in multiple pulse width modulation means more than one pulse we are going to get in a period of 0 to pi in the output voltage. If you are going to get more than one pulse period of 0 to pi in the output voltage, then we are going to call this as the multiple pulse width modulation. So here reference signal we are going to use the same thing as the previous one, which is the square wave, whereas the carrier signal we are going to use the triangular waveform. The one more thing is sine pulse width modulation. The name itself indicates that the reference signal is we are going to use the sine waveform, whereas the carrier signal we are going to use the triangular waveform. So I have already told you the reference signal can be either square or sine, whereas the carrier signal always triangular. So based on this, we are going to, based on this comparison of the triangular signal, or you can say based on the comparison of the reference signal and the carrier signal, we are going to generate the pulses to trigger the thyristors or to trigger the switches which are fully controllable. So based on that we are going to get the output voltage waveform, and then we are going to have a variable value of the output voltage we are going to get with the help of this pulse width modulation. So single pulse width modulation means only one pulse in a period of 0 to pi. So therefore in the half of the period means 0 to pi, only one pulse we are going to get in the output voltage, and also the reference signal is square signal and the carrier signal is triangular waveform. Whereas in multiple pulse width modulation, here we are going to get more than one pulse we are going to get in half of the time period, or 0 to pi, the output voltage we are going to get. Here we are going to use the reference signal as square wave, whereas the carrier signal as a triangular waveform. Similarly, in the sine pulse width modulation, the name itself indicates here we are going to use the reference signal as the sine waveform, whereas the carrier signal we are going to use the triangular waveform. So based on this, we are going to get means we are going to use the reference as sine wave. So based on this we are going to get some output voltage graph we are going to get. So based on the output average value also we can easily variable. So the only thing, the main agenda of this pulse width modulation is we can remove some of the harmonics. So with the help of pulse width modulation we can eliminate some of the harmonics which we don't want. So we can remove those harmonics which we don't want in the output voltage, and also we can vary the overall output average value also we can vary. So this is the benefit of using the pulse width modulation. I am repeating again, with the help of this pulse width modulation we can remove whatever the harmonics that we don't want in the output voltage, and also here with the help of this thing we can also control the average value of the output voltage also we can control with the help of this pulse width modulation. So let me tell you some of the important advantages of this pulse width modulation. So the output voltage will varies with change in pulse width. I have already told you. So now by changing the pulse width, now we can easily vary the overall average value of the output voltage. Whereas in the previous case we are going to get a constant voltage irrespective of the load. We are going to get a constant output voltage waveform. So no matter whatever the load, we are going to get the constant voltage waveform is constant average output voltage we are going to get, but we don't want that. We want a variable output average voltage we need. So with the help of this pulse width modulation, the output average value is going to get changed. So output voltage will vary with change in pulse width. So as you vary the pulse width, then definitely you can vary the average value of the output voltage. And the frequency of the output will change by changing the reference signal frequency only. Just by changing the reference signal frequency. So very important point. By changing the frequency of the reference signal. So just by changing the frequency of the reference signal, then definitely we can change the frequency of the output signal. So listen carefully. By changing the frequency of the reference signal only, we can change the frequency of the output signal. So the frequency of the output signal or the output voltage will change only by changing the reference signal frequency only. So only by changing the frequency of the reference signal only we can vary the frequency of the output voltage. It's a very important statement, and based on this statement some of the questions have been already asked in the A examinations. So I am going to specify it more and more. So therefore the frequency of the output voltage is going to depend only on the frequency of the reference signal. So as you vary the frequency of the reference signal, then definitely the frequency of the output voltage is also going to get changed. So the frequency of the output voltage will change by changing the reference signal frequency only. Reduction in the THD will with selection of proper pulse width. So reduction in the THD with proper selection of the pulse width. So reduction in the THD with selection of proper pulse width. I have already told you, if you want to eliminate some of the harmonics in the output voltage, then you can easily get the required pulse width in order to eliminate that harmonic in the output signal. So listen carefully. If you want to eliminate some of the harmonics in that output voltage, then the only thing is you have to choose that particular value of the pulse width so that you can easily reduce that harmonics or remove that harmonics from this output voltage. So if you want to remove any harmonic from the output voltage, then you have to go for the specific value of the pulse width in the output voltage. So if you apply that at one, definitely you can remove that harmonic from that in the output voltage. Basically we are going to get three advantages. Means with the help of PWM we can simply say that now we can simply say that the advantages of the PWM are very simple, which is now we can easily control the average value of the output voltage, and also the frequency of the output signal is going to purely depend upon the frequency of the reference signal, or simply we can say that the output frequency of the output voltage, or we can say the frequency of the output voltage is equal to the frequency of the reference signal. And also here we can remove some of the harmonics that we really want, that we really don't want. So we can remove it by choosing the proper pulse width. So means we can also remove the THD, total harmonic relation, also we can easily remove that. So these are some of the advantages by using this PWM technique. So now we are going to discuss about the single pulse width modulation. So now we are going to discuss about the single pulse width modulation. So the single pulse width modulation means here in the half of the time period the output is going to have only one pulse. That is called the single pulse width modulation. So now here I have already told you the reference signal we are going to use here as the square wave, whereas the carrier signal we are going to use the triangular waveform. So this is called as the carrier signal. So this is called as the carrier signal. I have already told you the carrier signal waveform is triangular in nature. So this is the carrier signal which is in triangular in format. Whereas the reference signal we are going to use which is a square wave. So we are going to use the reference signal as the square wave. So this is the signal that we are going to use here. So now I am going to compare the reference signal and also the carrier signal. And I have already told you we are going to give the reference signal to the, we can say that we have given the reference signal to the non-inverting terminal, whereas the carrier signal we have given to the, so we have given to the inverting terminal. I have already told you whenever the non-inverting terminal voltage is greater than the inverting terminal voltage, then the output will be plus VCC. Otherwise, if the non-inverting terminal is more than, so listen carefully, one thing I am repeating again, if the non-inverting voltage is more than the inverting voltage, then definitely the output we are going to get which is plus VCC. Otherwise we are going to get the output as 0. So you can see clearly only in this range we can see clearly that the magnitude, only we have to go for the positive value, means only go for the only positive nature. So therefore the magnitude of the reference signal, or we can say the magnitude of the reference signal is more than the carrier signal. So therefore during this amount of time period the output will be plus Vc, means here the amplifier output will be plus Vc and is going to give, means it is going to trigger the pulse generator. So therefore we are going to get the pulses Ig1 and Ig2 in the range of this period only. So only in this time where the magnitude of the reference voltage is greater than the magnitude of the carrier signal, then we are going to get a pulse of, means the pulse generator is going to generate a signal which is Ig1 and Ig2. So these are the triggering pulses which are given to the thyristor T1 and T2 of pulse with P. So this is the pulse with P. So therefore now here you can see clearly, here also you can see clear in this region which is the magnitude of the reference signal is greater than the magnitude of the carrier signal in this time period. So here also we are going to generate the pulses which are the Ig3 and Ig4 only in this time period. So therefore we have to go only for the magnitude part. So therefore simply we can say that here also we are going to generate the triggering the pulses Ig3 and Ig4. So these pulses we are going to trigger the thyristor T3 and thyristor T4, whereas here these pulses we are going to trigger the T1 and T2. So basically these pulses we are going to give to single phase full bridge voltage source inverter. So single phase full bridge voltage source inverter, we are going to give this triggering pulses to that circuit. Then we are going to see what is the nature of the output we are going to see. So whenever we give Ig1 and Ig2, then if you are going to give Ig1 and Ig2 triggering inputs, then we can say simply the output voltage is equal to plus Vs. So whenever we are going to trigger Ig1 and Ig2, means T1 and T2 if you are going to trigger, then definitely the output voltage is equal to plus Vs, because it is a single phase full bridge voltage source inverter. So therefore the output voltage is equal to plus Vs with a pulse width of P during this pulse period. So we can say now we are going to trigger thyristor 3 and thyristor T4. So whenever we are going to trigger T3 and T4, then we are, whenever we are going to trigger the switches T3 and T4, then we can say simply say that the output we are going to get which is minus Vs. So minus Vs we are going to get in this pulse. So only for half of the time period. So you can see only for half of the time period. So only for half of the time period it is going to have only one pulse. So the output is going to have only one pulse in half of the time period. Then we are going to call this as the single pulse width modulation. So this is called single pulse width modulation, means in the output only for half of the time period we are going to get only one pulse. So it is called as a single pulse width modulation. So I have already told you, means reference signal we are going to use basically here square wave we are going to use, and the carrier signal we are going to use the triangular waveform. And let us now do the analysis of this single pulse width modulation. So now I want to do the analysis of this circuit diagram, or we can say for these graphs I want to do the analysis of this circuit. So here Ig1 and Ig2 and Ig3 and Ig4 given to single phase full bridge voltage source inverter, then we get V0 output. I have already told you Ig1 and Ig2 and Ig3 and Ig4, we are going to give these triggering pulses to the switches. So therefore now in this single phase full bridge voltage source inverter, so based on this we are going to get the output voltage that we have got. And here M is called as the modulation index. M is the ratio of the peak value of the, so M is the ratio of the peak value of the reference signal by peak value of the carrier signal. It's a very important point. M is the ratio of the peak value of the reference signal by the peak value of the carrier signal. So M is the ratio of the peak value of the reference signal by the peak value of the carrier signal. So M is called as a modulation index. So here I will say from the graph we can say that always AR is always less than AC. If AR is less than AC only, if whenever AR is less than AC, so simply we can say that if AR is less than AC only, then only we can say that we can generate a pulses. Otherwise we are going to get like the same thing that we have discussed. See here AR should be always less than AC, then only we are going to get pulses in the 0 to pi period. Otherwise we are going to get the output which is similar to the first circuit, means then no need of doing the pulse width modulation. So if this is the case, then only it is good to get the pulses. Otherwise what we are going to get, suppose if AR is greater than AC, then always if AR is greater than AC means we can say that AR is given to the non-inverting. So non-inverting terminal voltage will be always greater than inverting terminal. So output will be always positive. So therefore the triggering pulse will be always given for all the time in the 0 to pi. So therefore the output voltage will be equal to Vs for all the time. So then we can't get the whatever the voltage output average voltage we want. So therefore definitely AR should be always less than AC, then only we can get the pulse in a given time period of whatever width we want. So therefore always AR should be always less than AC. So therefore AR should lie between 0 to AC. So this is the range of the AR. If AR is less than AC means definitely M is less than 1. So therefore M is going to lie between 0 to 1. So therefore if M is going to lie between 0 to 1 means the pulse width is going to lie between 0 to 1. Suppose if M is equal to 1 means we are going to get P is equal to 5. If M is equal to 0 means we are going to get P is equal to 0. So here M is called as the modulation index. It is a ratio of the AR by AC. So AR is going to lie between 0 to AC. So therefore M is going to lie between 0 to 1. So therefore the pulse width is going to lie between 0 to pi. Suppose if M is varying from 0 to 1 means simply we can say the pulse width is going to vary from 0 to pi. So now the average output voltage. So average output voltage will be. So I have already told you, see whatever the positive pulse area is equal to negative pulse area for the output voltage. So therefore the average value is equal to 0. So average value of the output voltage is equal to 0. So if you want to find what is the RMS value which is of the output voltage, which is Vs into under root over P by pi, or we can say 2B by 2 pi. So Vs into under root over 2P by 2 pi. So we simply it is Vs into under root over P by pi is the RMS value of the output voltage. So by changing frequency of reference signal, the frequency of output changes. So if you try to change the frequency of the reference signal, then simply we can say that the output of the, or we can say the frequency of the output is going to get changed. So by changing the frequency of the reference signal, the frequency of the output changes. So this point you can see from the graph itself. So you can say clearly, see as you change the frequency of the reference signal, so the reference signal is square wave. So if you try to change the frequency of the reference signal, then definitely the frequency of the output signal is also going to change. Means whatever the output frequency is equal to the frequency of the reference signal. So therefore simply see only this triangular pulse is going to give you the pulse width. Only this triangular pulse is going to help you to give a pulse width in 0 to pi, but it is not going to change the frequency. So if you want to change the frequency, then change the frequency of this reference signal. So if you change the frequency of this reference signal, then we are going to change the frequency of the output signal, or simply we can say that the frequency of the output signal is equal to the frequency of the reference signal. So the frequency of the output signal is equal to the frequency of the reference signal. And one more thing is, if you try to change the frequency of the carrier signal, then you can only change from 0 to pi. You can only change the number of pulses. only you can change the number of pulses but not the pulse width, which is 0 to pi. So 0 to pi will be always constant. 0 to pi will be only changed when if you are going to change the frequency of the reference signal. So if you change the frequency of carrier signal, the only thing that you are changing is the amount of pulses in 0 to pi. So therefore simply we can say that if you change the frequency of the reference signal, then definitely the frequency of the output signal also changes. Or simply we can say that the frequency of the reference signal is equal to the frequency of the output signal. Whereas if you change the frequency of the signal, the only thing that you are changing is here you are only changing in a period of 0 to pi. In the range of 0 to pi, you are only changing the number of pulses you are changing. Only that thing that you are going to get by varying the frequency of the carrier signal. By changing the reference signal frequency, you are going to change the output signal, or simply the frequency of the output signal is equal to the frequency of the reference signal. So as you can see clearly, the output voltage is a, or we can say, periodic signal. So as it is a periodic signal, so if you want to try to express in terms of Fourier series, the final expression that you are going to get, which is V0 is equal to sigma n is equal to 135 up to infinity 4 Vs by n pi into sin n pi by 2 into sin np by 2 into sin n theta. So this is the expression that you are going to get finally, which is V0 is equal to sigma n is equal to 135 up to infinity 4 Vs by n pi into sin n pi by 2 into sin np by 2 into sin n theta, where p is called as the pulse width of single pulse, means the pulse width of the signal in the range of 0 to pi. So in the range of 0 to pi, the pulse width of the output signal is p. So therefore V0 is equal to sigma n is equal to 135 up to infinity 4 Vs by n pi into sin n pi by 2 into sin np by 2 into sin n theta. So here you can see it has only harmonics, means only odd harmonics are going to present, 1, 3, 5, 7 like that. Only odd harmonics are going to present in the output voltage. So if you want to eliminate the nth harmonic component, suppose if you want to eliminate any nth harmonic component, simply what you have to do is here you have to make this term to 0. So if you want that term, so if you don't want that harmonic to be present in that output signal, then definitely you have to equate this term. This sin np by 2 is equal to 0. So np by 2 is equal to k pi. So k into pi. So therefore p is equal to 2 pi k by n. So this is the pulse width. So the p is going to lie between 0 to 180 degree only. So the value of p only lies from 0 to 180 degree. So n is not equal to 1. So n is not equal to 1 because the fundamental component will be always going to present. So therefore n is always not equal to 1. So n can lie from, so except 1, the remaining values are 3, 5, 7, 9, 11, 13 like that. So here k can go from any value, which is 1, 2, 3 and goes on. So you can't go for the fundamental. See, you cannot remove the fundamental component. Always fundamental component frequency is going to present, but the remaining harmonics are, except fundamental, the remaining everything is called as a harmonics. So only those terms that you can remove. So n can be either 3, 5, 7 and goes on, and k can be any value, which is 1, 2, 3 up to infinity. So therefore here the p value should be always lying between 0 to 180 degree. So therefore simply sin np by 2 is equal to 0, means np by 2 is equal to k pi. So therefore sin k pi is equal to 0. So therefore p is equal to 2 pi k by n. So n cannot be equal to 1, means n can be 3, 5, 7 and goes on, and k can be 1, 2, 3 up to infinity. So p is going to lie between only 0 to 180 degree. So 180 degree is the maximum value. So with the help of this equation, means if you go for this amount of pulse width, then definitely you are going to remove that value of nth harmonic. You are going to remove from this overall output voltage. So V0 is equal to V0 of t is equal to sigma n is equal to 135 up to infinity 4 Vs by n pi into sin n pi by 2 into sin np by 2 into sin of n omega t. So if you want to find what is the fundamental value of the output voltage RMS value, so if you want to find what is the RMS value of the fundamental output voltage, which is the fundamental component is, substitute here n is equal to 1, so we are going to get 4 Vs by pi into sin pi by 2, which is 1 into sin p by 2. So take the another term root 2. So divide by root 2, we are going to get finally 2 into root 2 Vs by pi into sin p by 2. So this is the value of the RMS value of the fundamental component of the output voltage, and the fundamental displacement factor is equal to, as there is no delay, so cos 0 is equal to 1. So therefore this is the fundamental power factor or fundamental displacement factor. So if you want to find what is the distortion factor, which is equal to the ratio of the RMS value of the fundamental component of the output voltage by overall RMS value. So you know the value of this RMS value of the fundamental component voltage and also RMS value of the overall voltage. So this value which is just now we have figured out, and the RMS value of the overall output voltage, which is simple, which is Vs into under root over 2p by 2 pi. So then if you substitute here, and finally you are going to get this expression, which is 2 into root 2 by under root over p into pi sine of p by 2. So this is called as the distortion factor. And if you want to find what is the input power factor, it is a product of the distortion ratio into fundamental displacement factor. So you know the value of G and you know the value of fundamental displacement factor. So if you do the multiplication, we are going to get which is equal to G itself, because FDF is equal to 1. So 2 into root 2 by under root over p5 into sine p by 2. So this is the input power factor. And if you want to find what is the value of the THD, total harmonic distortion, which is equal to under root over 1 by G whole square minus 1. So you know the value of G, substitute here, and if you do simplification, finally you are going to get the total harmonic distortion is equal to this is the value that you are going to get. So now we are going to learn the multiple pulse width modulation. So multiple pulse width modulation means simply here in a given period of 0 to pi, means in a given period of 0 to pi, you are trying to increase the number of pulses in the output voltage. That is called as the multiple pulse width modulation. Means if there are more than one pulse in 0 to pi range in the output voltage, then it is called as the multiple pulse width modulation. So in the multiple pulse width modulation, I have already told you the reference signal we are going to use the square wave, whereas the carrier signal we are going to use the triangular waveform. So here now you can see clearly, now we have increased the frequency of the carrier signal, or we can say we have increased the frequency of the carrier signal. So by increasing the frequency of the carrier signal, I have already told you, by increasing the frequency of the carrier signal, we are going to increase the number of pulses in a given half of the time period. So in a 0 to pi, we are going to get more number of pulses. That is we are going to get with the help of increasing the frequency of the carrier signal. But the frequency of the reference signal is same. So therefore, we are not going to change the frequency of the output signal, as because the frequency of the output signal is equal to the frequency of the reference signal. So because of that, they both will be same. Only by increasing the frequency of the carrier signal, you are going to increase the number of pulses in a given half of the time period in the output voltage. I have already told you here, whenever the reference signal voltage, the magnitude of the reference signal voltage is greater than the magnitude of the carrier signal, then only the output of the amplifier op amp will be plus VCC. So it is going to trigger the IG1 and IG2. So therefore, only in this range you can see clearly that the magnitude of the reference signal is greater than the magnitude of the carrier signal. So therefore, simply we can say here we are going to get the output voltage is plus VC, or we can say we are going to get here triggering of IG1 and IG2. Similarly, here also, here the reference signal, the magnitude of the reference signal is greater than the magnitude of the carrier signal. So here also we are going to get trigger the T1 and T2 switches, or we can say switch S1 and switch S2 we are going to trigger in this period. So let me assume both the pulses having the same pulse width, which is P and P. So here also we can see the magnitude of the, in the reverse, or you can say the negative cycle, that we can say simply here the magnitude of the reference signal is greater than the magnitude of the carrier signal. Here also, and also here also, the magnitude of the reference signal is greater than the magnitude of the carrier signal. So therefore, only in this period also we are going to trigger the switch T3 and switch T4. So we are going to get, let me assume both are having the same equal pulse width of P and P. So therefore, simply we can say that here IG3 and IG4 means we are going to trigger the thyristor T3 and thyristor T4 here, whereas in this case we are going to trigger thyristor T1 and thyristor T2. So in 0 to pi we are going to trigger, during these periods we are going to trigger T1 and T2. During this period we are going to trigger T3 and T4, both simultaneously at this instance. So whenever T1 and T2 are triggered, whenever T1 and T2 trigger, then definitely, so here whenever here T1 and T2 trigger, so therefore the output voltage is equal to supply voltage, so which is plus Vs. Here also T1 and T2 are triggered, so therefore the output voltage is equal to plus Vs, so plus Vs. Similarly here we are going to trigger T3 and T4, so output voltage is equal to minus Vs, and here we are going to trigger again T3 and T4, so therefore the output voltage is equal to minus Vs. So now we are going to get the output in terms of pulses, and this is the half of the time period. So you can simply see here, by increasing the frequency of the carrier signal, we are going to only increase the number of pulses in 0 to pi in the output voltage. But whereas the frequency of the output signal is equal to the frequency of the reference signal. So only thing that you need to remember is always the frequency of the reference signal is equal to the frequency of the output voltage signal, whereas by increasing the frequency of the reference, by increasing the frequency of the carrier signal, we are going to increase the number of pulses in half of the time period of the voltage signal. So as there are more than one number of pulses, in 0 to pi, so we can say this is called as a multiple pulse width modulation. What I told you, VR is called as a reference signal. Here we are going to use the square wave in the multiple pulse width modulation, whereas VC is called as the carrier signal. We are going to use here triangular waveform. So let me do the analysis of this multiple pulse width modulation. See, as the positive area is equal to negative area in the output voltage, so therefore the average value of the output voltage is equal to 0. And if you want to find what is the RMS value of the output voltage, which is Vs into under root over 4p by 2 pi. So 4p by 2 pi is nothing but we are going to get 2p by pi. So Vs into under root over 2p by pi we are going to get. In general, the RMS value of the output voltage is equal to Vs into under root over mp by pi. Or simply we can say 2 mp by 2 pi, means simply we are going to get mp by pi, where m is called as the number of pulses in half cycle. So m is called as the number of pulses in half cycle. So m is called as the number of pulses in half cycle. So m is called as the number of pulses in half cycle, which is m into p by pi. So Vs into under root over m into p by pi, where m is called as the number of pulses in half of the cycle. So m is called as the number of pulses in half of the cycle. And if you want to find what is this value of m, or you can go for any value which is p or q. M is called as the number of pulses in the half cycle. So m is called as it is a ratio of the fc by 2fr. So fc by 2fr is called as the m is equal to fc by 2fr. So this is going to give you the number of pulses we are going to get in the half of the cycle. In the half cycle, how many number of pulses we are going to get in the output voltage we are going to get through this expression, which is fc by 2fr, where fc is called as the frequency of the carrier signal, where fr is called as the frequency of the reference signal. So always fc will be always greater than fr. Then only what we are going to get, then only we are going to get multiple signal. Then only we are going to get the multiple signal. Otherwise we are going to only single pulse. So when fc is greater than fr, then only we are going to get multiple pulses in 0 to pi, in 0 to half cycle. In half cycle we are going to get more number of pulses if fc is greater than fr. Otherwise we are going to get only one pulse. So m is equal to fc by 2fr is going to give you the relation, means it is going to tell you the number of pulses which are present in the half cycle in the output voltage we are going to get. So always the frequency of the reference signal is equal to the frequency of the output voltage signal, whereas by increasing the frequency of the carrier signal we are going to increase the number of pulses in half cycle of the output voltage. So m is equal to fc by 2fr, where m is called as the number of pulses in the half cycle in the output voltage we are going to get. It is equal to fc by 2fr, where fc is the frequency of the carrier signal and fr is called as the frequency of the reference signal. See, and already I have told you the modulation index is equal to ratio of AR by AC, where AR is called as the peak value of the reference signal, whereas AC is the peak value of the carrier signal. So always AR is less than AC. So therefore m is going to lie between 0 to 1. So P is going to lie between 0 to pi. If AR is greater than AC, then definitely for all the time we are going to get the plus Vs, output voltage is equal to plus Vs. Then you are not doing any average voltage changes. So with the help of PWM we are going to change the output average voltage, and we can even reduce the harmonics. Also we can even eliminate them. So now we are going to learn about the sinusoidal pulse width modulation. Sinusoidal pulse width modulation means here simply we can say that in the sinusoidal pulse width modulation, here I have already told you, in the sinusoidal pulse width modulation we are going to take the reference signal as the sine wave, whereas the carrier signal we are going to consider the triangular waveform. So this is called as the square sine wave we are going to use for the reference signal, whereas for carrier signal we are going to use the triangular waveform. So for reference signal we are going to use the sine waveform, whereas for carrier signal we are going to use the triangular waveform. Already I have told you, always the peak value of the reference signal should be always lesser than the peak value of the carrier signal. So therefore this is the wave I am going to consider. So only in this region, I have already told you, only in this region the magnitude of the reference signal is greater than the magnitude of the carrier signal. So therefore we are going to generate a positive pulse. Similarly here also we can see clearly, the magnitude of the reference signal is greater than the magnitude of the carrier signal. So here also we are going to generate a signal of pulse. So therefore let me assume the first pulse of pulse with P1 and the second pulse is of pulse with P2. These are going to trigger the both T1 and T2 switches. Whereas here, the negative cycle you can see, here also the magnitude of the reference signal is greater than the magnitude of the carrier signal, and here also the magnitude of the reference signal is greater than the magnitude of the carrier signal. So here also we are going to generate a negative pulse, or you can say we are going to trigger the both T3 and T4 in this negative pulses of the sinusoidal, or you can say sine curve. So in the 0 to pi we are going to trigger, so during this pulse with us P1 and P2 we are going to trigger T1 and T2, and during this negative cycle we are going to trigger both the thyristors T3 and T4 with the pulse width of P1 and P2. So here in this positive cycle, in the positive region of 0 to pi, we are going to trigger both T1 and T2 with the pulse width of P1 and P2. So in the pulse width of P1 we are going to trigger T1 and T2, so therefore the output voltage is plus Vs during this pulse with P1. Similar here also we are going to trigger both T1 and T2 with the pulse width of P2, so therefore the output voltage is equal to the supply voltage with the pulse width of P2. Similar here also we are going to trigger the T3 and T4 with the pulse width of P1, so whenever the T3, T4 we are going to earn, the output voltage is equal to minus Vs, the pulse width of P1. So whenever we are going to trigger T3, T4 with the pulse width of P2, then we are going to get the output voltage as minus Vs with the pulse width of P2. So this is the output voltage that you are going to get finally. So you can see clearly here the frequency, as you are going to increase the frequency of the carrier signal, then definitely you are going to get more number of pulses in the half of the cycle of the output voltage. Whereas the frequency of the difference signal is equal to the frequency of the output voltage. So therefore you can see this is called as the same point I have already told you. So always the frequency of the output voltage is equal to frequency of the difference signal. Whereas by increasing the frequency of the carrier signal, we are going to increase the number of pulses in half of the output, in half of the cycle of the output voltage. So already I have told you simple concept here. VR is called as the reference signal. We are going to use sine wave in this sinusoidal pulse width modulation, whereas VC is called as the carrier signal. Here we are going to use the triangular waveform in the sinusoidal pulse width modulation. So now let us do some analysis of this sinusoidal pulse width modulation. As the positive area is equal to negative area in the output voltage, so therefore the overall average value of the output voltage is equal to 0, and the RMS value of the output voltage is equal to Vs into under root over 2 into P1 plus P2 by 2 pi. So simply we are going to get Vs into under root over P1 plus P2 by pi. So this is the thing that you are going to get finally. So this is the very important points. So now we are going to learn about the three-phase voltage source inverter. Three-phase voltage source inverter means here basically we are going to use input as AC, but output we are going to get. So see here input we are going to use DC and output we are going to get three-phase AC. So here simply we are going to convert a DC source into a three-phase AC source. So output we are going to get three-phase AC supply we are going to get at the output. So that is called as a three-phase voltage source inverter. So basically the inverter means here inverter is going to convert a fixed DC voltage into a variable frequency of AC voltage. So listen carefully, inverter basic operation is to convert a fixed amount of DC voltage into a variable frequency of the output voltage. As I have already told you how to get the variable frequency, by changing the frequency of the reference signal we are going to change the frequency of the output. So therefore simply we can say that inverter the basic function is to convert a fixed DC into a variable AC of variable AC means we can simply say that the inverter means the basic function of inverter is to convert a fixed DC voltage into a variable frequency of AC voltage. Now here we are going to use see this is the circuit diagram of this one. So by the circuit diagram we are going to convert a fixed DC into AC voltage, three-phase AC voltage we are going to get. So T1, T4, T3, T6, T5, T2. So T1, T2, T3, T4, T5, T6. So three legs we are going to use here. Three legs. So three legs of these thyristors we are going to use, and at these 2 points we are going to take it output A, and from these 2 points we are going to take it output as B, and from these 2 points we are going to take it as C. So here we are going to connect a three-phase balance load. So let me take each balance load means all the impedances are of same value, R. So they are connected in a star fashion. So these are the points A, B, C. So from this we have connected to three-phase balanced load which is connected in a star manner, and this is the point is neutral N. So this is T1, T2, T3, T4 and T5 and T6. So this is the circuit diagram of the three-phase voltage source inverter. So by this we are going to convert a fixed DC into a three-phase AC source we are going to get at the output. So this is the balanced load we are going to connect at the output of this inverter. So there are two modes of operations are possible, which are the first one is 180-degree mode of operation and the other one is 120-degree of mode of operation. So in this circuit, in this three-phase voltage source inverter, we are going to get two modes of operations. One is the 180-degree mode of operation and the other one is the 120-degree mode of operation. So these two mode of operations that we are going to get in this three-phase voltage source inverter, one is 180-degree mode of operation and the other is the 120-degree mode of operation. Now let us discuss the first one, which is the 180-degree mode of operation. So now we are going to study the 180-degree mode of operation. So here each thyristor connects for only 180 degree. So each thyristor is going to connect for only 180-degree mode. That is the thing. That is the reason we are going to call this as the 180-degree mode of operation. Means each thyristor in this circuit is going to connect for only 180-degree time. So only for this range it is going to connect. So each thyristor it is going to connect for only 180 degree. So because of this only we are going to call this as the 180-degree mode of operation. So see now this is the scale of 360 degree. I am going to consider a scale of 360 degree. So for each thing I am going to divide into 30 30 30. So 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330 and 360. So in the first leg there are T1 and T4. So in the first leg there are T1 and T4. So from 0 I am going to consider 180 degree. So 0 to 180 is T1 it is going to connect, and from remaining 180 to 360 T4 is going to get connect. So simply in the first leg there are T1 and T4 thyristors. So T1 is going to connect from 0 to 180, whereas T4 is going to connect from 180 to 360. So the difference means T1 is going to connect for 180-degree mode of 180-degree range, and T4 is going to connect for 180-degree range. Similarly, now what I am going to do is now I am going to shift from 120 degree. So I am going to do from 120 degree. So from 120 in the second leg there are T3 and T6 thyristors. So from 120 plus 180, which is 120 to 300. So 120 plus 180 is nothing but simply we are going to get 120 plus 180 is 300. So therefore from 120 to 300 T3 is going to get connect. So T3 is going to connect, and in the similarly from 300, so 300 plus 180 is nothing but 480. So therefore 300 to 360 plus 0 to 120. So this overall range 120 plus this 60, which is again 180. So this overall range is connected by T6 thyristor. So simply we can see that so T3 is connecting from 120 to 300 and T6 is connecting from 300 to 480, or simply 300 to 360 plus 360 0 to 120. And similarly now in the third leg there are T5 and T2. So in the third leg there are T5 and T2 thyristors. So T5 is connecting from, so again shift by 120 means from 240. So from 240 a 180-degree range is connected by T5, and then the remaining range is connected by the T2. So this is the way that you need to remember. So T1 means from 0 to 180, again T4 means 180 to 360. Similarly, if you want T3 means just a shift of 120 degree. So from 120 degree to 300 T3 is connecting, and the remaining range is connected by the T6. So if you want the T5, so from 240, so from 240 to the range of 180 T5 is connecting, and the remaining range is connected by T2. So this is the very simple thing. So the only thing is here phase shift of 120 degree. So each thyristor is going to connect for 180 degree mode. So each thyristor is going to connect for only 180 degree range. So now I am going to find what is the output voltage I am going to figure out. See, I am going to find three voltages, which is VAN, VBN and VCN. So this we are going to call it as the VAN, VBN and VCN, we are going to call this as the phase voltages because it's a star load. So therefore VAN, VBN and VCN it is called as the phase voltages, and the line voltages are the VAB, VBC and VC are called as the line voltages. So now I want to find what is the value of VAN, VBN and VCN. These are the phase voltages. So now I am going to see for 60 degree. So for every 60 degree I am going to see how many number of thyristors are going to get connected. So for every 60 degree how many number of transistors are going to connect, and I am going to see what is the range. So you can see clearly for 0 to 60. So for 0 to 60 you can see clearly T1, T6 and T5 are connecting. So T1, T5 and T6 are connecting. So whenever the T1, T5 and T6 are going to connect, then try to analyze this circuit. So then try to analyze this circuit and try to find what is the value of VAN, VBN and VCN. So then we are going to get VAN is equal to Vs by 3 we are going to get, and VBN we are going to get minus 2Vs by 3, and VCN we are going to get, which is Vs by 3. So these are the voltages that you are going to get after doing the analysis from 0 to 60 degree. Again from 60 to 120 degree. So you can see clearly from the circuit itself T1, T6 and T2 are going to conduct. So if you try to analyze by on the T1, T2 and T6, and if you try to analyze, then we are going to get VAN is equal to 2Vs by 3, and VBN is equal to minus Vs by 3, and VCN is equal to, you are going to get minus Vs by 3. That's the thing we are going to get. Again from 120 to 180. So from 120 to 180 you can see clearly T1, T3 and T2 are going to conduct. So T1, T3 and T2 are going to conduct. So if you try to analyze this circuit by on these switches, and if you want to find what is the value of VN, VBN, VCN, then VN is equal to Vs by 3, and VBN is equal to Vs by 3, and then VCN is equal to minus 2Vs by 3. These are the voltages that you are going to get. Again after this 180 to 240, so for every 60 degree you are going to try to find what is the value of these voltages. So again for 180 to 240, then you can see clearly from this diagram itself. So from 180 to 240, so T4, T3 and T2 are going to conduct. So if you try to analyze when by owning the T3, T4 and T2, then you are going to get VAN as minus Vs by 3, and VBN as 2Vs by 3, and VCN as minus Vs by 3. These are the voltages that you are going to get. Again from 240, so again from 240 to 300. So if you try to see from this diagram, so you can see clearly T4, T3 and T5 are going to conduct. So if you try to analyze the circuit, then after that we are going to get VAN as minus 2Vs by 3, and VBN as Vs by 3, and VCN as Vs by 3. So again these are the voltages that you are going to get. Again the last one, which is from 300 to 360. So if you try to analyze from 300 to 360, you can see clearly that T4, T6 and T5 are going to conduct. So if you try to analyze by owning these switches, and if you try to find what is the value of VAN, VBN, VCN, then we are going to get VAN as, we are going to get minus Vs by 3, and VBN as minus Vs by 3, and VCN as 2Vs by 3. So these are the voltages that you are going to get finally. So by owning the switches, so by this phenomena, by the switches, we are going to draw VAN, VBN and VCN. So we have got all the diagrams. So by these values we have plotted a diagram. So this is called as, this is the diagram that you are going to get. So VAN, VBN and VCN you are going to get. After analyzing, you are going to get VAN, VBN and VCN. So after this, what you are going to do simply is, here suppose if I want to find what is the VAB, so line voltage, so VAB is equal to VAN minus VBN. So if you do the difference of these two graphs, then you are going to get, so this is the line voltage VAB you are going to get. So this is called as the cos square waveform. So this is called as the cos square waveform, whereas these are the stepped square waveform. So these are the stepped signals. It's like steps. These are like steps. So this we are going to call it as the stepped wave. These are the phase voltages are the stepped waveform, whereas the line voltage is a cos square waveform. So listen carefully. The phase voltages are in the shape of the stepped waveforms, whereas the line voltage is in the format of the cos square waveform. So if you want to find what is the value of the peak to peak voltage, so peak to peak voltage in this, so peak to peak voltage in the phase voltages is equal to, so the peak to peak voltages in the phase voltages is equal to, so in the phase voltages the peak value is 2Vs by 3 and the negative peak is minus 2Vs by 3. So if you do the subtraction, the positive peak minus negative peak, the overall peak to peak value is 4Vs by 3. So for all the phase voltages, the peak to peak value is 4Vs by 3. Whereas for line voltages, the peak to peak value is here plus Vs and minus Vs. So if you go for peak to peak, it is equal to 2Vs. So listen carefully, the peak to peak the peak to peak voltages of the phase voltages is 4 Vs by 3, whereas the line voltages, the peak value is 2 Vs. So we can simply say that always the peak to peak voltage of the phase voltages is simply which is 4 Vs by 3, whereas the peak to peak voltage of the line voltage is 2 Vs, and the phase voltages are in the stepped square waveform, whereas the line voltage is in the quasi square waveform. So if you try to remember this graph, if you try to remember this graph Van, then you can shift it by 120, then you are going to get Vbn, and then you shift it by again 240. So if you shift by 120, you are going to get this waveform. If you shift this waveform by 240, then you are going to get Vcn. So just we are going to shift it. So therefore, if you remember this Van, then by shifting it by 120, we are going to get Vbn, and by shifting it off 240, then we are going to get this waveform Vcn you are going to get. So this is Vs by 3, 2 Vs by 3, again Vs by 3, again minus Vs by 3, again minus 2 Vs by 3, again minus Vs by 3, again repeating to Vs by 3. So listen carefully, plus Vs by 3, 2 Vs by 3, minus Vs by 3, minus Vs by 3, again minus 2 Vs by 3, again minus Vs by 3. So again it is repeating. So if you try to shift it by 120, you are going to get this signal. Again if you try to shift by 240, you are going to get this signal. So Vs by 3, 2 Vs by 3, Vs by 3, minus Vs by 3, minus 2 Vs by 3, minus Vs by 3. So shifted by 120, you are going to get this waveform. Shift by 240, we are going to get this waveform. So if you do the subtraction of these two waveforms, Van minus Vbn, we are going to get Vab with a peak value of plus Vs and minus Vs. So the peak to peak value, the peak to peak voltage of this line voltage is equal to 2 Vs, and the peak to peak voltage of this phase voltage is 4 Vs by 3. So 4 Vs by 3 is the peak to peak voltage of the phase voltages, whereas the peak to peak value of the line voltage is 2 Vs. So now we are going to do some more analysis of this 180-degree mode of operation. So some more analysis that we are going to do for this 180-degree mode of operation, which is for each 60 degree there are 3 SCRs will be connecting. Yes, I have already told you, for every 60 degree there are 3 SCRs are going to get connected. So for every 60 degree there are 3 SCRs are going to connect at a time. So for every 60 degree there are 3 SCRs are going to connect at a time. So nature of output voltage, output phase voltage is stepped square waveform. I have already shown you Van, Vbn and Vcn. So these are the graphs which are going to have a stepped square waveform. So therefore the nature of output phase voltages is a stepped square waveform. See, I have already told you for Van, which is plus Vs by 3, then plus 2 Vs by 3, again plus Vs by 3, again minus Vs by 3, again minus 2 Vs by 3, again minus Vs by 3. So this is the format it is going to get repeat. For every nature of output line voltage is quasi square form. Already I have told you that the nature of the output line voltage is a quasi square waveform. Whereas peak to peak voltage of the output line voltage is 2 Vs. I have already told you the peak to peak voltage of the output line voltage is 2 Vs, whereas the peak to peak voltage of the output phase voltage is which is 4 Vs by 3. I have already told you. And so if you try to find what is the average value, of either phase voltage or the line voltage, always it is equal to 0, because the positive area is always equal to negative area. So always, whether it is a phase voltage or whether it is a line voltage, always the average value is equal to always 0, because the positive area is equal to negative area. So if you try to find what is the RMS value of the phase voltage, so RMS value of the phase voltage. So if you try to find what is the value of the RMS value of the phase voltage, then finally you are going to get root 2 Vs by 3. So root 2 Vs by 3, this we are going to get. So root 2 Vs by 3, this is the thing that we are going to get for the phase value of the RMS value of the phase voltage. Whereas the line voltage is equal to, so if you try to find what is the RMS value of the line voltage, if you try to find what is the value of the RMS value of the line voltage, then finally we are going to get under root over 2 by 3 into Vs. So under root over 2 by 3 into Vs we are going to get. So the RMS value of the phase voltage which we are going to get, which is root 2 Vs by 3, whereas the RMS value of the line voltage is under root over 2 by 3 into Vs. So the easy way to remember, which is VL RMS is equal to root 3 into V phase RMS, because as it is a star load, so therefore the line voltage is equal to root 3 times of phase voltage. So as it is a star load, so therefore the line voltage is equal to root 3 times of phase voltage. So similarly, the line voltage RMS is equal to root 3 into V phase RMS. So even if you remember one RMS, then by using this relation you can figure out the other value. And I recommend to remember this line voltage RMS value. So the line voltage RMS value, which is under root over 2 by 3 into Vs. So if you remember this one, you can easily get the value of this value also. So the line voltage RMS value is under root over 2 by 3 into Vs. So the line voltage RMS value is equal to under root over 2 by 3 into Vs. So the line voltage RMS value is equal to root 3 into V phase RMS. So V line RMS is equal to under root over 2 by 3 into Vs. So V line RMS is equal to under root over 2 by 3 into Vs. So power consumed by 3-phase balanced load. So now how much amount of active power consumed by this 3-phase balanced load, which is in the star fashion. Then how to figure out this one? So simply P is equal to 3 into V phase RMS square by R. So V phase RMS square by R is going to tell you the amount of power consumed by single phase, but there are 3 phases, so into 3. So this is going to give you the amount of average power consumed by this 3-phase balanced load, which is 3 into V phase RMS whole square by R. So 3 into V phase RMS whole square by R. So 3 into V phase RMS whole square by R. You can easily get these values. So therefore, I have already told you VL RMS is equal to under root over 2 by 3 into Vs, whereas VL RMS is equal to root 3 into V phase RMS, and the power is equal to 3 into V phase RMS square by R. So now, as the line voltage is a periodic signal, or it is a cos square waveform, then I can easily write the expression. I can easily write the Fourier series expression for this line voltage. So now we are going to find what is the expression of the line voltage. So the line voltage expression is, say, as I've already told you, the line expression is it is basically a periodic signal. So whenever there is a periodic signal, we can write in terms of the Fourier series. So finally, after writing the Fourier series, we are going to get the expression, which is sigma n is equal to 135 up to infinity 4 Vs by n pi into sine of n pi by 3 into sine of n theta plus n pi by 6. So this is the overall expression that you are going to get after the line expression, which is VL is equal to sigma n is equal to 135 up to infinity 4 Vs by n pi into sine of n pi by 3 into sine of n theta plus n pi by 6. So this is the overall expression of the line voltage. And if you want to find what is the expression of the phase voltage, so if you want to find what is the expression of the phase voltage, so phase voltage, there are also periodic signals, so you can write in terms of Fourier series, which is V phase is equal to sigma n is equal to 135 up to infinity, which is 2 Vs by n pi into sine n theta. So V phase voltage is equal to sigma n is equal to 135 up to infinity 2 Vs by n pi into sine n theta is the expression of the phase voltage, whereas this one is called as the expression of the line voltage. So you can see clearly the line voltage is free from 3n harmonics. So if you substitute the value of n is equal to 3, here you are going to get sine pi, which is 0. So all the 3n odd harmonics are going to absent. So all the 3n odd harmonics are going to absent in the line voltage. So we can say that in the line voltage, all the 3n odd harmonics are going to become 0. So therefore, this is the meaning of this one. So the line voltage is free from 3n harmonics, and the minimum harmonic frequency present in the line voltage is, so the first fundamental is 1 and the next harmonic is 3. So 3 is going to absent. The remaining harmonic is 5. So 5 is called as the minimum harmonic, which is going to get present. So therefore, the frequency of the minimum harmonic is equal to 5 times of f, where f is called as the fundamental frequency. So therefore, the minimum harmonic present in the line voltage in the 180 degree conduction mode is, which is 5 into L. So frequency of the minimum harmonic is equal to 5 into f. So where f is called as the fundamental frequency. So now I want to find what is the value of the G. So G is called as the ratio of the, so G is for line voltage. I want to find what is the value of the distortion factor. It's a ratio of the fundamental. So I want to find what is the value of the G for the voltage, for the line voltage. So basically for line voltage, I want to find what is the value of the harmonic distortion factor. So G is equal to VL, or you can see it is a ratio of the RMS value of the fundamental line voltage by the overall RMS value of the line voltage. So as we already know the value of VL, so I have already told you the VL RMS, the line voltage RMS value, which is under root over 2 by 3 into Vs, and also we know the expression of the line voltage. So the fundamental value RMS is simply substitute n is equal to 1. So 4 Vs by pi into sine of pi by 3 by under root over 2. So if it is simplification, finally we are going to get 3 by pi. So line voltage is taken into account, means we are going to take the line voltage. So for the line voltage we are going to find the value of the distortion factor, and if you know the value of G, then THD is equal to under root over 1 by G whole square minus 1. So you can substitute in place of G, and if you solve this one we are going to get 31%. So the THD is equal to 31% you are going to get for this line voltage. So now we are going to study about the 120-degree mode of operation. So for the same circuit, now we are going to study what is the 120-degree mode of operation. Means for three-phase voltage source inverter. So for this three-phase voltage source inverter, now we are going to study what is the 120-degree mode of operation. Means each thyristor is going to connect for only 120 degree. That is the meaning of this one. So each thyristor is going to connect for only 120 degree. That is the meaning of this 120-degree mode of operation. So therefore I am going to draw 3 lines with respect to theta. So for each an angle of 30. So I have already told you T1 is going to connect for only 120 degree. So the remaining 60 will be absent, means it is 0. It is not at all connecting. Again, so from overall 180, see up to 120 it is going to connect. The remaining period it is not at all going to connect. Again, from 180, T4 is going to connect for 120 period, and the remaining 60 it is going to become absent, means it is not at all going to connect. And similarly, take a phase shift of 120. So from 120 go for again 120. So therefore simply we can say that here it is going to up to 240. So T3 is going to connect for only 120 to 240, and the remaining 60 it is going to become 0. And remaining again from 300, T6 is going to connect for only 120, and the remaining 60 degree it is going to become absent, means not connecting. Similarly from 240 again T5 is connecting for 120 degree, and the remaining 60 is going to become absent. And T2 is going to become from 120, and the remaining 60 is going to become absent. So from overall 180 only 120 is going to connect, and the remaining period it is off. That is the meaning of this one. So take a phase shift of 120, again take a phase shift of again 120. So you are going to get this one. Same as the previous one, but only thing is here out of 180 only 120 degree mode it is going to conduct, and the remaining 60 degree it is going to become off. That is the meaning of this one. So each thyristor is going to connect for only 120 degree in this 120 degree mode of operation. So now based on the switching, now we are going to draw what is the phase voltages and also the line voltages. So you can see clearly for every 60 degree now we are going to calculate the values. So for every 60 degree we are going to calculate what is the phase voltages and also the line voltages. So you can see clearly from 0 to 60, T1 is conducting, T6 is conducting. Only these two thyristors are going to get conduct. So T1, T6 are going to get conduct. So therefore if you do the analysis by switching, by on the T1 and T6 thyristors, then by solving it we are going to get the line voltage, the phase voltage and the line voltage we are going to get. So we are going to get the VAN is equal to Vs by 2, and VBN we are going to get minus Vs by 2, and VCN we are going to get which is 0. So these are the voltages that you are going to get after doing the analysis from 0 to 60 degree. Similarly from 60 to 120 degree, so you can see clearly T1 is connecting and T2 is connecting. So when you on the T1 and T2, after analysis you can get the phase voltages and the line voltages you can easily get. So VAN is equal to Vs by 2, and VBN is equal to 0, and VCN is equal to minus Vs by 2. So this is the thing that you are going to get. Again from 120 to 180, so you can see clearly T3 is conducting and T2 is conducting. So therefore T3, T2 are going to conduct. So whenever the T3, T2 are going to conduct, you can analyze the circuit, and then finally you are going to get the phase voltages and the line voltages. So VAN is equal to 0 you are going to get, and VBN you are going to get Vs by 2, and VCN you are going to get minus Vs by 2. So these are the voltages that you are going to get. Again from 180 to 240, so you can see clearly T4 and T3 are going to conduct. So only T4 and T3 are going to conduct. So after that we are going to get VAN is equal to minus Vs by 2, and VBN is equal to plus Vs by 2, and VCN is equal to 0. So this is the voltage that you are going to get. Again from 240 to 300, so for every 60 degree we are going to calculate. Again you can see clearly T4 and T5 are connecting. So if you analyze the circuit by switching the T4 and T5, after finally you are going to get which is Vn is equal to minus Vs by 2, and Vbn you are going to get 0, and Vcn you are going to get plus Vs by 2. So these are the voltage that you are going to get. Again from 300 to 360. So again from 300 to 360, you can see clearly here T6 and T5 are conducting. So whenever the T5 and T6 are going to conduct, then try to analyze what is the value of Van, Vbn and Vcn and Vab. So here Vn, Vbn, Vcn you are going to get finally, which is Vn is equal to 0, and Vbn is equal to minus Vs by 2, and Vcn is equal to plus Vs by 2. So now you know all the values of the phase voltages. So now simply plot all these graphs. So therefore you are going to get Van, Vbn and Vcn. So based on analysis, we have drawn all the phase voltages Van, Vbn and Vcn. So now I want to find what is the line voltage Vab, Vbc and Vca. So Vab is equal to Vbn minus Van minus Vbn. So Vab is equal to Van minus Vbn. So if you do the subtraction of these two graphs, we are going to get this is the graph that you are going to get. So you can see clearly here the phase voltages are now cos square waveform. The phase voltages are the cos square waveform, whereas the line voltage is the stepped square waveform. This is opposite for the 180 degree mode of operation. So you can see clearly here now the phase voltages are the cos square waveform, whereas the line voltage is a stepped square waveform. And if you want to find what is this graph, so simply just remember for every 60 degree, so plus Vs by 2, plus Vs by 2, 0, minus Vs by 2, minus Vs by 2, 0. Then try to shift for 120 degree. So you are going to get this graph. Again shift by 120, again you are going to get this graph. So simply if you remember this one, then go for shifting of this one for 120, you are going to get this one. Again shift this by 240, you are going to get this graph. So everything is same. So only thing is you are shifting it. So if you remember this one graph you can get easily Vbn and Vcn. So simply I can say that here this is called as the Vs by 2, Vs by 2, 0, minus Vs by 2, minus Vs by 2 at 0. So this is the way that you need to remember for every 60 degree. So these are the cos square waveform, whereas if you want Vab, just go for the subtraction of Van minus Vbn, then you are going to get like this stepped square waveform. So if you want to find what is the peak to peak voltage, so peak to peak voltage of the phase voltages. So peak to peak value of the phase voltage is equal to very simple. This is Vs by 2 and this is minus Vs by 2. So peak value which is a Vs. So Vs is the peak to peak voltage of the phase voltage. But if you want to find what is the peak to peak value of the line voltage, here the peak value is plus Vs and the negative peak value is minus Vs. So overall peak value is 2 Vs. So 2 Vs is the peak value of the line voltage, whereas the Vs is the peak value of the phase voltage. So Vs is the peak value of the phase voltage and 2 Vs is the peak value of the line voltage. And I have already told you here now the phase voltages are in the shape of the cos square waveform, whereas the line voltages is in the form of a stepped square waveform. So the easy way to remember is this one for every 60 degree Vs by 2, Vs by 2, 0, minus Vs by 2, minus Vs by 2 at 0. Now we are going to do some more analysis of this 120 degree mode of operation. So we are going to do some more analysis of this 120 degree mode of operation. So for every 60 degree there are 2 SCRs will be conducting, whereas for 180 degree mode of operation for every 60 degree there are 3 SCRs are going to conduct. But for this 120 degree mode of operation for every 60 degree only 2 SCRs are going to get conduct. So for each 60 degree there are only 2 SCRs will be conducting. And the nature of output phase voltage is cos square form. Already I have told you the phase voltages are in the shape of a cos square waveform. So the nature of output phase voltages is in the format of the cos square waveform, whereas the nature of output of the line voltages is stepped square form. I have already told you the line voltages will be in the form of a stepped square waveform. And see, whenever the positive ray is equal to negative ray for both the line voltage and also the phase voltage, so therefore the average value of the phase voltage is equal to 0 and the average value of the line voltage is equal to 0. Suppose if you want to find what is the RMS value of the phase voltage, so if you try to figure out RMS value of the phase voltage from the graph itself, so finally we are going to get Vs by root 6 we are going to get. So Vs by root 6 we are going to get, and the line voltage RMS value if you want to find from the graph, finally you are going to get Vs by root 2 you are going to get. But only thing is that you need to remember, which is the simple general expression is the line voltage RMS value is equal to root 3 into line voltage with phase voltage RMS value, because the load is connected in a star fashion. So therefore the RMS value of the line voltage is equal to root 3 times of RMS value of the phase voltage, and I told you to remember only the line voltage RMS value. For the previous case, the line voltage RMS value is under root over 2 by 3 into Vs, whereas for here it will be Vs by root 2. So the line voltage RMS value is equal to Vs by root 2. So this is the only thing that you need to remember. So the line voltage RMS value is equal to Vs by root 2, whereas for the previous case the line voltage RMS value is equal to under root over 2 by 3 into Vs, whereas for here the line voltage RMS value is equal to Vs by root 2. So if you know this expression, if you substitute here, you can easily get the phase value RMS also, you can easily get it. So now as the load is connected in a star fashion, I want to find what is the balance load. I want to find how much amount of average power consumed by this three phase load I want to figure out, which is 3 into V phase RMS square by R. So V phase RMS square by R, it is going to give you the power consumed by one phase. But there are three phases, so go for multiplication of 3 to get this value. So therefore V phase RMS whole square by R. So therefore 3 into V phase RMS square by R, you are going to get the overall power consumed by this three phase balanced load. So now I have already told you the phase voltages are in the cos square waveform. So as these are the periodic signal, simply you can write the expression of this Fourier series sigma n is equal to 135 up to infinity 2Vs by n pi into sine of n pi by 3 into sine of n theta plus n pi by 6. So whenever the signal is in the format of the cos square waveform, I have already told you here simply the odd 3n harmonics are going to get absent. So whenever the voltage is in the format of a cos square waveform, then definitely 3n odd harmonics are going to get absent. So if you substitute n is equal to 3, here you are going to get sine by, which is 0. And if you substitute n is equal to 9, again you are going to get 0. So therefore I already have told you, whenever the signal is in the format of a cos square waveform, then always 3n odd harmonics are going to get absent. And the line voltage is in the stepped square waveform. So we are going to, these are also periodic signal. So after writing the Fourier series, we are going to get n is equal to 135 up to infinity root 3 into 2Vs by n pi into sine of n pi by 3 into sine of n theta plus n pi by 3. So this is the expression that you are going to get for the stepped square waveform also. So here also you can see there is a sine n pi by 3 term is there. So simply we can say that here as it is a sine n pi by 3 term. So simply here also 3n odd harmonics are going to get absent. So 3n odd harmonics are going to get absent for here also. So simply both the line voltages and the phase voltages are free from 3n odd harmonics. So because of this component only, then we simply say that all the 3n odd harmonics are going to absent in both the phase voltages and also the line voltages. Whereas in the 180 degree mode of operation, only in the line voltage it is absent, but not in the phase voltages. So for that 180 degree mode of operation, the 3n odd harmonics are going to absent only for the line voltages. Whereas for this 180 degree mode of operation, 3n odd harmonics are going to absent for both the phase voltages and also the line voltages. So therefore the minimum harmonic present existing in the output voltages of both phase and line is fifth harmonic, because 3 are going to absent means the minimum harmonic, the next one is fifth. So fifth harmonic is the minimum harmonic that is going to present in both the phase voltages and also the line voltages in the 180 degree mode of operation. So I want to find what is the value of the distortion factor when I am going to take the phase voltage as the reference. So I want to find what is the value of the distortion factor when I want to take the phase voltage as the reference value. So it is a ratio of the fundamental RMS value of the phase voltage by the overall RMS value of the phase voltage. So simply you know the value of phase voltages, so go for the overall RMS value just now we have figured out, and if you want the fundamental value of the RMS value, just substitute n is equal to 1 and by root 2. So therefore 2Vs by pi into sine of pi by 3 by root 2. So if you do the simplification, finally we are going to get 3 by pi. So 3 by pi we are going to get, and Th3 is nothing but under root over 1 by g whole square minus 1. So if you substitute here, we are going to get 31%. So So the distortion factor is equal to 3 by pi and the TH3 is equal to 31%. So in this 120 degree mode of operation, that you need to only remember is simply here in the both the phase voltages and also the line voltages, all the 3 and odd harmonics are going to get absent. Whereas for our 180 degree mode of operation, only in the line voltage only, we can say that these 3 and odd harmonics are going to get absent, but not for the phase voltages.